One to N.
Is it a question?
That's a question from Charlie just now.
Okay.
So, because it said basically gives you 0 down.
If you visualize it here, I can visualize it on the other.
Yeah. So, yeah, go ahead and change it from 1 to N.
Okay. This wasn't a discussion.
Yeah.
This is good if you just said t minus 1.
Well, A is still 0. Is the problem.
Yeah, it seems
Oh, yeah, that's right. A times t. Okay. Sorry for the delay.
I'll go ahead and close an answer.
Oh, it's not even on.
Okay, sorry.
But it's good. Okay. So, all right. So we've talked about now different kinds of flow algorithms for computing max flow, and we've seen both the basic Ford-Fulkerson method. We've seen problems with the method, and we've also seen ways to fix these problems using different algorithms. Unlike with many of the other things we've discussed in class, the thing with flows is that we're not going to spend a huge amount of time anymore discussing the exact running time of the different algorithms for flows. And it's not that because this isn't an important question. And in fact, as I said, some of the project topics involve better algorithms for computing flows. It's a very interesting question. But it's just that from the purpose of what you can take away from an algorithms class when you learn about flows, what's even more interesting than the actual running time required to solve a flow problem is the fact that you can use flows to model many kinds of questions. So in some sense, flows are a good example of a modeling tool, where if you have to go out and solve some other kind of problem that has different characteristics, flows are a good way to model it. And all the hard work that you will find, and you'll see the next 2 lectures, is really about how to map a problem into a flow problem. And then you just invoke some standard algorithm, whether it's Ford-Fulkerson or some other clever algorithm. So the study flows in this class is really about how to think of flows as a modeling tool. And this is also true for divide and conquer and then programming, but there it's a bit more direct. And there the modeling is directly linked with the ability to run it efficiently. But there's no point doing a divide and conquer if you can't divide things roughly in half, and that comes directly in the running time. But here, the 2 things are somewhat more separate. And so today and in the next lecture, we're going to look at different ways in which you can model problems using flow and therefore solve them in ways that otherwise would not have been entirely obvious to you. And probably the most important example of this is one we're studying right now, which is called Magix. Okay, I'll explain what that means. We will also look at today other ways you can take a problem that looks like a flow problem but with extra constraints on it and change it a little bit so it becomes a flow problem. And again, for those of you who may be familiar with the idea of linear programming and the fact that max flows are a special case of a linear programming problem, this should not be surprising because roughly speaking, as long as you have linear constraints that don't involve squares and cubes and stuff, you can more or less transform a problem into another one. But if you're not familiar with linear programming, this will seem like something that's very cool. And it is very cool because that means that you can take the fact that you can change a different kind of problem into a flow problem means that you now have a large collection of applications where you can now apply. So I'm saying all this to you. We won't actually see the applications till the next lecture. Today we're just going to build up some more muscles, if you will, to sort of deal with flows. And the first big muscle we're going to develop is one called matching. So what is the problem of computing a matching? It's actually a very simple problem. Okay. So in a problem of matching, and the simplest version, there are more general cases. You're given what is called a bipartite graph. Hopefully you know what a bipartite graph is. It's a graph which you can divide the vertices into two parts, a left and a right if you wish, and all edges connect one side to the other, but they won't connect things inside the same side. And a bipartite graph like this, you have edges between them. Okay. And the goal of the matching problem is to compute some kind of pairing between nodes on the left and nodes on the right. So this set of red edges is a pairing because every node on the left has exactly one pair on the right and vice versa. So formally a matching is a subset of edges in a graph so that no two edges have anything in common. And a particular example of a matching, this one is called a perfect matching. It's called perfect because every node on the right is matched to something on the left and vice versa. Now this may not always be possible. I could remove an edge. Suppose I remove this edge from the graph. If I remove this edge from the graph now, if I now try to find a perfect matching that matches everything, I might struggle a bit. I might end up with a matching that looks like this. Now this is also a matching because again it's a subset of edges, one that connect left to right, and no two edges overlap on a vertex. So it is a matching. Is it perfect? No, because now we don't have the connection from this one right there to a neighbor. There's no way to connect them up. But you can't make this, but if you look at it carefully, you'll realize that if you look at the size of this matching, the number of edges of this graph, number of edges in the matching, which is 4. In the previous case it was 5. 1, 2, 3, 4, 5. And now it's 4. You can't add another edge to this because I've removed that one edge. You can't actually change this matching, throw things out, put things back in to make it bigger. So the underlying question that we're always going to be looking at is how do you find a largest possible matching? So that will be called a maximum matching. In some cases the matching will also be perfect, in which case we have covered everything. So a matching of size n in a graph with two sets of size n will be a perfect matching. Because the two sides are different sizes, or you don't have a matching of size n, it will be called a maximum matching if it is maximum, but it will not be perfect. Yes?
Quick question. In maximum matching, perfect matching is not possible with the edges given? Or?
Well, for a given graph, there's always some matching that's maximum,
Yes.
even if it's trivial, even if it's 0.
Yeah.
It may not always admit a perfect match. So for example, if I have a graph consisting of one edge and another edge,
Okay.
in a trivial way there's no way this can be perfect because there's just different number of vertices on each side. There are two vertices on this side, one vertex on this side.
Yeah.
That's a trivial way of saying there's not a perfect match. That's a bit silly. But you can construct examples like this with the same number of vertices on each side, but there isn't a perfect. I could remove a bunch of edges, for example.
My question is, if I take out the red one and take some other way, and if I can get a perfect matching,
Yeah.
would this be called maximum matching?
No, it would not. Exactly. It would because it's not maximum.
Because it's not matching.
Yeah. However, there is another name for a matching like that can't be made any bigger. So let's say that I decided to swap out some edges. So I took off that edge there, and I replaced it by this edge here, and in the matching. Okay. I did this. So I get something that looks like this. Okay. This is also, let's see. Right, so this matching, 1, 2, 3, it's got only 3 edges in it. It's got even one less than the previous one. Notice. So the previous matching had 4, this one has 3. Right? The claim though is that I cannot make this any bigger just by adding things to it. So if you look at trying to add any edge, any edge you add will collide with one of the edges that's already in the set. So even though I know that there's a better way to do this matching, that I could have got a matching of size 4, there's no way to increase this matching to make it size 4. I'll have to delete something and then add something and so on and so forth. This matching is called maximal. It's maximal because I cannot increase it any further just by adding things to it. It's not maximum because I know there is something bigger. So if you think of greedy algorithms, right? So in this landscape and we're trying to find the highest point, a maximal matching is like a local max. You get to the top of some little hill. A maximum matching is the highest point in the region. You could get to a local matching, a local maximum, so that's maximal, but you can't get up there because you're going to go down to the maximum. You think of the landscape. So in some sense, if you have a maximal matching that's not maximal, that means there's no greedy step to get you to the maximal matching. This is a clue, by the way, that you may not be able to use a greedy algorithm to find maximum matchings because you could get stuck with this.
Excuse me.
Yes.
Maximum matching is when we can cover all points in right side.
So that's a perfect matching. Because perfect. Everything's fine.
And so
Maximum is just the biggest possible. So perfect matching has to have a certain size. It has to have size equal to the size of one of the two sets. A maximum matching could be any size, but it's the biggest possible. You've thought very hard, you've done your optimization, you can't get any bigger. A maximum matching is one that cannot be grown. Given the set, I'm kind of stuck. I can't get any further. It's a local maximum. So it's local versus local. Okay, these are just names. They're names, and like all names, it might take a while to get used to. So don't worry if you're having a hard time keeping track of it right now. Your ability to do problems and matching is not going to be not going to depend on your understanding of the difference in the words, but it will be something that will be useful later on. Maximal matchings have nice properties and so on. Okay, so I've defined a matching in a bipartite graph. And again, you can define a matching, by the way, in a general graph that's not bipartite. It's the same thing. A set of edges that are disjoint that pair things up. But things get a little bit harder. So we're going to stick to bipartite graphs for now just to get it done. And so, one question you could ask is, where would I ever come across in practice, since I claim these things are useful in practice, such a problem? And if you think about it, matchings are kind of everywhere. So, for example, you have a freshman class and you have to pair up people into rooms. You have some matching problem. Okay. Of course, that matching problem is not going to be bipartite, right? Because you may have gender divided dorms, but then anyone can potentially pair up with anyone in a room. So that's one thing. You could have, for example, when med students apply to med school, there's this after they finish med school, there's this residency program where there are med students on one side and there are residency programs on the other side, and again they have to be matched up. Now again, you could say, well, that's not technically the same thing because you could have many students going to one hospital, but you can imagine each slot in the hospital being numbered. So there's slot number 1, slot number 2, slot number 3, and then you want to match them all up. And so any kind of situation where you have to assign objects to other objects, or assign things to other things, or assign people to things, or assign things to people, you're going to get a matching problem. Okay. And if two things are of different kinds, you're going to get a bipartite matching problem. Right? So you have to assign things of type A to things of type B. You're not going to assign things of type A to each other. And you'll see that there are direct applications of the kind I mentioned. There are more indirect applications where it's more subtle, but you still have to solve a matching problem. And so the question then becomes, how do we do this? How can we go about solving a problem of computing a maximum or a perfect matching? By the way, how would I compute a maximal matching graph? Do I need to know anything special to compute a maximal matching? What might I try to do?
Have a greedy.
What do greedy?
I take whatever nodes, I take the edges, whichever edges I take a vertex or edges, and then keep taking down the vertices which are done every time. I'll be left with few vertices which cannot be combined, and then I have a maximum.
Okay. Any other methods? This is a vertex-based approach. Is there any other based approach? How would I do this? I mean, forget about greedy, right? Even something even simple. I mean, it is kind of greedy, but it's even simpler than that. So here's an algorithm. I have this graph, I take an edge, any edge. Once I've taken it, its endpoints are done. I can't touch them anymore. So I throw them out along with all edges going to it. It's very similar to this. I take another edge, and I do it another one. I take another one. I don't care how I pick them, I just pick them. This will give me a maximal matching, because at some point I will stop, and I can't go any further. Whether it's a good matching or not, I don't know, but it will be maximal. So you can often get something very, and in fact, this algorithm, just pick an edge and then pick another one, pick another one, it's actually quite good. There's a certain precise way that I can say how good it is, but we won't be able to talk about it later. So if you want to compute just a maximum matching, it's not very hard. If you want something that's maximum, you have to think a little bit more. All right. So we would like to solve, since we're in the flow section of the class, we're thinking we'd like to solve this using flows. And we know that a flow problem has a couple of characteristics. First of all, it's a directed graph. It's not an undirected graph. So if you want to model this problem using flows, we've got to somehow make it directed. And for lack of any better ideas, if you have a left and a right, that seems like it suggests a direction. So we'll put a direction on all the edges. So all edges will be directed from left to right. Now a flow problem also has two more things to it. It has a directed graph. What else does it have? So I'm hearing source sinks. I'm hearing capacities. Okay. So a source and sink. Well, the source and sink, and we have directions already, so it suggests, okay, let's just kind of add a source and a sink this way. So there's a source, there's a sink. We don't know what the source should connect to, so we'll just connect to every one on the left. Why not? We have a sink, we don't know who should connect to it, but all the stuff on the right is getting stuff coming into it, so maybe they should all connect to it. So now I have a graph, a directed graph with source and sinks. And of course, as you all pointed out, we need capacities. So we should add some capacities. I don't know what the capacity should be. So let's make all the capacities 1. Why not? Again, I say why not? Not because this is the right answer, but because it's a good first step. And as we'll see later on, sometimes this is the best way to start, and you'll find out it's not working and you change things around. But for now, we'll just stick with this and see what happens. So now I have an actual complete instance of a flow problem, right? And there is actually a better than arbitrary reason why I set all the capacities to 1. Why might 1 seem like it's a good idea for this problem?
Because if I take
Oh, it matches the problem we were doing earlier, so that every node, you can only choose one outgoing edge.
Ah, very good. So the argument here is the following. If every edge coming in and going out of a node has capacity 1, right? And we know that when we push the flow, we're going to get an integer flow. What is effectively going to happen? What's effectively going to happen is that when we push this flow through the graph, you're going to be, the algorithm is going to be forced to pick one of the outgoing edges of a vertex in order to send any flow on that it gets. It's going to be forced to pick one incoming edge of a vertex to send flow to it. We have no choice in the matter because all the capacities are 1. So by saying the capacities are 1, we have capacities to be 1, we have encoded the idea that you can only have one edge that's active coming out of a node and one edge that's active coming into a node, which is essentially what the matching constraint is. Right? So we run some flow algorithm and we get some flow. And based on the intuition that we just had, we can say, well, what is the resulting object that we want? We're going to look at all the edges, the real edges, not the fake ones we put in. We're going to look at all the real edges that have flow on them. And we're going to say any edge that has a flow of 1 is part of our matching. So in this case, you have a flow that looks like this. These are the edges that are going to be claimed to be part of the matching. I say claimed because I haven't shown that in fact this is a matching or not. Okay. That make sense? So first of all, is that correct? Forget about sizes and this and that. Is it in fact a matching? So in order for it to be a matching, we have to say that no two edges will intersect. No two edges of common endpoint. And as we just argued, if any two edges of common endpoint, whether it's a tail or a head, that means that either there are two units of flow flowing into a vertex, or there are two units of flow flowing out of a vertex. Right? But all the vertices that can have flow going into them on the left side have only one edge coming in with capacity 1. There's no way they can have 2 units of flow going out. Any vertex on the right side that has 2 units of flow coming into it has only one edge going out of it. So there's no way it can carry 2 units of flow coming in. So it's not possible for 2 edges to overlap at the same vertex. So we know the set of edges we get in fact forms a matching. We don't yet know if it's any better than just an arbitrary matching, but we know it forms a matching. We can also ask, what is the value of the matching? Well, what is the value of the flow? If the flow was of value k, then there are k units of flow going out from the source. The matching size must be also k. So in other words, what we've said is that if you want to compute a matching of size k, you set up all these flow problems and then see if you got a flow of size k by running Ford-Fulkerson, whatever you want. And because maximizing the flow will maximize the matching, right? And every flow gives you a matching. And conversely, so this is not enough, by the way. I said every flow will give you a matching. So the max flow will be some matching. But is it possible that maybe the maximum matching is not a flow? I cannot achieve it using a flow? So we have to show that not just every flow, which I just argued give you a matching, that every matching gives you a flow. Suppose, conversely, I have a matching in the graph that looks like this. Can I extend it into an actual flow instance? Well, yes, because every matching satisfies all the capacity constraints on the edges it's using. So we can just extend flow backwards, forwards in an appropriate manner, and we'll get a flow of the same value. So we need these two facts. Every flow of size k gives you a matching of size k. Every matching of size k gives you a flow of size k. Which means that maximizing the matching is equivalent to maximizing the flow, because they're always equal. But we know to solve the max flow problem. So by solving the max flow, we have found the maximum matching. So that's it. The maximum matching problem is solved. Take the graph, add a source, add a sink, add extra edges, run the flow algorithm, wait. Any questions? Yes?
How do we know that this is the maximum matching? How do we figure out the maximum?
So, how do we know that this is the maximum matching? So this is what I was saying. So our algorithm is of the following form. It says, take the graph, extend it to a directed graph, add the source sink capacities, and run a max flow algorithm. We have already shown that every flow result will give you a matching, right? So we know that so if there's a max flow of size k, the maximum matching has cost at least k. That's what we've shown. That's enough. There's a lower bound. But we have to show the other side. That if there's a maximum flow of size k, the maximum matching is of cost at most k. And we argue that by saying that if you had a matching of size k, then there also exists a flow you can produce from it. And since Ford-Fulkerson or any other algorithm produces the max flow, it has to be able to produce this flow. May not be the exact same flow, but it'll be the same flow value, because I claim my algorithm can produce. Okay, so we're proving that the max flow is greater than or equal to the maximum matching and is less than or equal to the maximum matching. Therefore, the max flow is equal to the maximum matching. Okay. Yes? Okay. Okay. What is the running time of this algorithm? Well, total capacity emanating from the source is n. Let's say there's n vertices on each side. I don't know how many edges there are. So Ford-Fulkerson will be m times the total capacity, so it'll be m times n. It's maybe a little bit more, actually it's m plus 2n times n, because I've added some extra edges. M is usually bigger than n. The fact pipes algorithm, we said was m squared log f, so it'll be m squared log n. The short pipes algorithm would correspond to be m squared times n. And notice something interesting. I mean, all this fuss about how bad Ford Fulkerson is actually the best one here. That again was my point, that when we say one is worse than the other, I was merely pointing out that in the worst case it could be very bad. I didn't mean that for every single problem it could be very bad. In this particular case, because the total capacity is not large, it's only n, it actually works quite well. This is not optimal, by the way. You can actually do better than that. I think the best bound you can get is n times square root of n. But that's much more complicated. Takes a bit more work. So we're done. We have an algorithm that solves the maximum matching problem using flows. So this is the first example of how to apply flows to solve a problem that didn't seem like necessarily it had a flow-based solution. And if you think, well, this is an obvious thing and this should, this is not that hard to see that you should apply flows, you have the benefit of hindsight, sort of sitting in this class. Because I've actually talked to people who were trying to solve a problem that they didn't know was a matching problem, that they didn't realize till later on. And their solution was to basically brute force all possible permutations. And I'm not saying this to make fun of them, it's just that they didn't know that there was any better way of doing it because it was not obvious how to do it. So it's one of those things where it seems obvious when you see it in class, but it's actually not that obvious unless you have heard about flows before. All right. One of the interesting things about matchings is that, and this is maybe a little bit further away from flows, is that there's a very interesting property that allows you to go between when you have a perfect matching and when you don't. And so that's something I want to talk about next. There's a very famous theorem. It's called Paul's theorem. And it says, well, it says what it says. I'll just let you read it for a second. Just the theorem, don't worry about the proof. Oh, sorry, good point. This is a notation thing. Okay, gamma A is the set of all neighbors of A. So in particular, since this is a bipolar graph, gamma A is some subset of the right-hand side, Y. So it's all the neighbors coming. Okay. So the question that came up earlier was, well, how do we, maybe it came up, maybe not. How do we know if a graph has a perfect matching or not? And we can compute the maximum matching, the flow. We can say, oh, the maximum matching was of size. Actually, let me stop for a second. How do we check if a graph is a perfect matching? Forget this theorem. We've just seen it already. What do we do? If I give you a graph and say, does it have a perfect matching or not? How do I answer yes or no? Yes?
The size of A is same as the vertices on each side.
Exactly. So the size of A.
What is that A?
Oh no, forget A here. Forget this theorem.
The number of edges is same as the number of vertices.
Exactly. So if you run the max flow algorithm, and the output you get is the same as the number of vertices on one side, then it's a perfect matching. Easy. But suppose I didn't know anything about flows. How then would I tell whether a graph had a perfect matching or not? It seems like, okay, so this is a weird thing, right? I say that I can talk about a graph and I talk about a matching in a graph. And it seems like the existence of a perfect matching should be something to do with the graph itself. I shouldn't have to bring in this heavy machinery called max flows and all these algorithms and all this nonsense. Just talk about a graph. Right? And so this theorem, in some sense, and this predates a lot of what we know about flows, is a way of characterizing when a graph is a perfect matching without talking about flows and stuff. And what it says is the following. Suppose I have a graph, it's the same number of vertices on either side, of which there's no way it can have a perfect matching. And I want to know if it can have a perfect matching or not. Then either it does, okay, or there is some subset of vertices on one side, on the left side, whose neighborhood shrinks. Because the number of vertices in the neighborhood, gamma A, is less than the number of vertices in A. Now, having studied flows, this seems reasonable to you. Yeah, there's a bottleneck. A bottleneck is going to prevent things from pushing through. That seems kind of right. It's not a proof, but it seems okay. I can see that. But the statement is actually quite strong, right? It's not just saying that this will happen. It's an if and only if statement. It's saying that either for every subset it expands, in which case you have perfect matching, or there's one for which it doesn't, in which case you don't. So it's a very strong statement, and this is what's called Hall's theorem. And what we'd like to do is sort of try to prove the statement. And it turns out there are many ways to prove it. As with most sort of useful statements of this kind, there are multiple ways to prove them. There's one that's kind of this hideous proof by induction. Hideous and induction tend to go together. All induction proofs are hideous. But there's also a way to prove it using max flows, which is historically sort of doesn't make any sense because this theorem was well known before we talked about flows. But you can actually prove it fairly easily using max flows. And with most proofs of this kind, most if and only if proofs. So here's a meta theorem. If you ever have to prove that something is if A if and only if B, one of these two sides is usually easy. So you have to prove that if A then B and if B then A, right? Okay. So here I have to show that if the graph has a perfect matching, then this property is not true, and that if this property is true, then the graph does not have a perfect matching. So the easier case is say suppose the graph does have a perfect matching. Okay. So suppose the graph does have a perfect matching. Okay? So just compute this matching. Imagine this matching exists. Now look at every subset of vertices on the left side. So what can we say about its neighborhood? We know that the graph has a perfect matching. So for every node in this set, there is a corresponding match. Okay? So the neighborhood size is at least the size of the set. And there could be more. I don't know if there are, but there could be more. But I don't care. I'm done. If the graph has a perfect matching, then if you take any set on the left side and look at its matches, there will be at least as many things as this because it's a matching. I just take the match name. So that's very simple. And the real question, of course, becomes what happens the other way? Okay? So again, we're trying to prove what is essentially a very beautiful combinatorial characterization of when a graph has a perfect matching, namely Hall's theorem. And we're going to prove it using flows, at least for half of it using flows. And we only prove one side of it, which is the easy side. I'm going to prove this. Okay. So what we want to show now is that if the maximum matching is not perfect, so the size of the matching is less than the cardinality of x, then there must be some set on the right side, on the left side, that does not expand, that contracts, which shrinks them. Okay? So we need to show that there is some set of vertices, we need to find it somehow, that has a neighborhood that has smaller cardinality. Okay? Alright. So let's say you do have a matching, and it's a size less than x, less than n. And let's look at this matching here. So we want to find, so in this case in particular, we have a subset here that is small. We want to find it. So let's see. So let's look at the flow that corresponds to this maximum matching. Okay? And let's say that this, sorry, 1 second. Wait. Okay, hold on. Yeah, okay. So let's look at a corresponding flow. Wait, something wrong with this flow. Hold on. Yeah, this is the cut. But I'm trying to see what the corresponding flow was to give you this cut. So these are all the vertices you can, yeah, this is, okay, good. Yeah. Right. So let's say that there's a flow in the graph, okay, and that there's a corresponding cut. And this set here, A prime, this is the set of vertices. Yeah, so let's say these are the set of vertices in the cut on the left side of the graph here. So I have these vertices here, that's my cut. The red edges are the edges on which flow is going. These are the edges coming out of the cut, yes. So there's 1, 2, 3, 4 edges coming out of this cut. And so the flow, so yes, good. So the set of exercise is 5, and the flow value is 4. So the total cut capacity coming out of the cut is 4. In this case, let's say this is that cut. Okay, so this is a set of vertices not containing the sink, reachable from the source, and these are the edges emanating from the cut. Okay, the red edges are what emanating from the cut. Okay. Now this set contains vertices both on the left side and the right side. Right? So let's look at the vertices just on the left side of this cut, namely this set right here. Okay? Now, so let us say that there is a neighbor of A. So let's look at all the vertices in A. Okay? And let's look at their neighbors. Okay? So there are two kinds of neighbors of vertices in A. There are vertices that are still in the cut, like the one up there. And there are vertices that are not in the cut, like the one out there. Okay? And so this will help us in the argument a little later on. Let us move every vertex connected to an element of A that is itself not in the cut. So in particular, that one up there, that one up there, bring it into the cut. Okay? We'll just do, it's a counting argument, it's going to bring it in. This does not change the cut value, notice. Because each one of those vertices has one edge coming out of it, of capacity 1, going to the sink. So I can move this without causing any problems. I consume one edge bringing it in, but there's one edge more coming out. So the cut value does not change at all. So I can move this thing in, and I don't know why it would change. Okay, so yeah. So I move this one here like this. Okay? Alright. Okay. So now what? We keep doing this. And which means now once we finish doing all this, we can say something about all the edges that are coming out of the cut. Either they come out from the right side, right? Or they coming into the left side. There are no edges in between anymore in the cut. So they're either coming out from there to T, or they're coming from source to this. Right? So the total, if you add them all up, right? So there'll be, you have these many edges and those. So you have 2 plus 2. All right. So what? So now the question is, remember, what was our goal? Our goal was to find this set. A set of vertices whose neighborhood is small, right? And essentially, I'm going to claim this neighborhood is going to be this A right here. Right? We're getting it. Okay, so let me see if I have the argument right here. Yeah, okay. So the claim is now okay, good. So because of this transformation we did, we can now say that the neighborhood of A is a subset of the neighborhood of A prime because of the way we just pulled everything in. And so now all cut edges either leave the source or enter the sink. So the cut value is basically the intersection of X with, let's see, the intersection of X with the sink, with the right side, or with the, sorry, the pictures are much easier. So let me just quickly go back to the picture. So basically what I'm saying is that the total cut value is this much plus that much. Okay, that's all I'm going to say. Okay, and then if we add them all up, and again this is one of those things which is just a we know that there are only so many edges coming out of the sink, and there's only edges coming into the source. If you add up all the calculations, you'll find that the neighborhood size of A is going to be given by this. You get this expression. So again, I think I messed up this a little bit. But the calculation is very straightforward. Basically, the idea is that once you get the flow and you look at the cut value, you can actually find a cut whose size is going to be small. It's going to shrink. That's the subset that's size is going to shrink. And that's why the overall cut was going to be less than n. So another intuitive way of saying this, and this is how the inductive proof kind of works, is that if overall you can't push n units of flow, then you can keep looking at very carefully until you find a smaller set for which there was never a way to push at that units of flow. So if you have a big bottleneck, then there's going to be a small bottleneck. And again, you can prove this using flows, but without flows, it's a different. You have to come up with a very different reasoning. But the flows give you the intuition that this kind of thing should be correct, that there has to be a bottleneck somewhere if you're unable to push this. Okay. All right. So that's all I want to say for now about matchings, and we'll take a short break for a few minutes, and then I want to come back and tell you about other ways you can model flow problems. Okay. So we'll just take a short 5 minute break. Okay. So, brief announcement also, the lectures for the last couple of three, it took a bit of a while to get uploaded. They are uploaded now. I will make sure to link them to syllabus. In the meantime, if you're subscribed to the U of U data channel, you should automatically get a notification whenever they get posted. I think we're on the date till almost today. So, they're all available. And I will put links to syllabus. So I also hope you're all working on, I know from the questions and the discussion you're working on your homework, which is good. I also hope you're working on your project. Again, it's one of those things where it's easy to, I see some it's easy to kind of say, we've got plenty of time. And hopefully the lecture I gave you last week kind of showed you the amount of work you have to do just to grasp the basics of the material and how much extra reading you have to do around it. So I'm hoping that you're all kind of starting. I'm not going to ask and embarrass you, but consider this a sort of early signal. This may be a time to start at least skimming the paper, trying to identify where the gaps in your knowledge, things you might need to understand more about, other references you might need to line up to read. Okay? By I think today is the 30th? No, 30th, yeah. So I was going to say by the end of September. We're already at the end of September. So I think by the end of this week, you should definitely in your own minds have a list of other things you need to read to understand the paper. And you can only do that by skimming the paper first and figuring out where you're getting roadblocked and stuff. Some of them might be as simple as looking at Wikipedia. Some of them might be actual references. So try to make sure you do that by the end of the week. Okay, just it's a friendly warning, so because it'll be much harder later. Okay. Questions? Yes.
So I had another intuition about saying whether the graph has perfect matching or not.
Okay, good. Let's hear it.
So can you see the graph?
The graph. The graph.
Okay, so in this, if in our perfect matching, if we are going to have edges which are going up from x to y, if there are few edges like that, then we need to have same number of edges which are going down from x to y.
I don't know what up and down means.
Oh, sorry. So I mean, if you put the vertices in Euclidean two-dimensional plane, then it's like the edges which are going up are having positive slope.
You mean, wait, what? You mean
So
like
here
this?
you have,
You mean like this?
yeah.
But I could make them all have positive slope.
Sorry.
I could make all the edges go up. I could just move that one way up top of the page.
Then you're going to miss something in the y.
But I would change the graph just by moving, on my piece of paper, I draw them differently.
I mean, so have all the vertices at equal level of x and y.
So you have them all lined
At
up.
equal level, yeah.
Okay, yeah.
And then say if you are having in your perfect matching, if you are having some edges which are going up, then you need to have equal number of edges which are going down. Otherwise, you won't get a perfect.
I guess you don't mean down so much as not up. Because you're going straight across.
Yeah, so if you have,
I think I have a counter example to that. Like if you.
Well, wait, he hasn't fully specified the statement, so you can't, because he could just wriggle out very carefully. Since you've got to make him fully specified before you catch him. So are you talking about, what about straight across?
so
Is that up or down?
If you are having all the edges which are straight across, then you're not having. So the number.
But I'm just saying, when you say up, do you mean strictly down?
I'm saying up, as in here there are just two edges which are straight and others are all going up. So like.
Okay, so you do mean strictly down, strictly up. Okay, now, okay, hit it.
Let's just change the graph to have, so you've got 5 vertices, and let's say starting from the bottom going up, the first one just has an edge going, doesn't connect straight across, but it goes just up one.
Okay.
And then same for the vertex next, and the next one, and the next one, and then the top one goes straight down to the very bottom. So then you have 4 edges that would be connected straight across, and then one edge coming down. So
And it's a matching.
yeah, and it'd be a perfect.
Actually, instead of numbers, I should have said.
See, wriggling has started already, so.
Something like sum of slopes. Right? So,
Sum of slopes.
yeah.
Okay, and now I think you're in bigger trouble. You made it so that coming up with the counterexample will be a bit harder, which is clever. But I think you're gonna just completely get hosed now, because when you talk sum of slopes doesn't mean it's not even a well-defined notion. Right? I mean, what does it mean, sum of slopes?
I'm talking about in the picture when we are.
So let me ask you this. I think I don't mind so much whether your claim was wrong or not, but I'm interested in the way you're thinking about it. So somehow you're arguing that if I drew these things using geometry,
Yeah.
that gives me a clue.
Right.
So on the surface of it, I would say why? Because this is a graph. It has no geometry, intrinsic geometry to it. Why should I expect that looking at it geometrically, with slopes and stuff, should make any difference to the way I draw it? I could draw these edges with little squiggly lines. Every edge could be a little like that. And my algorithm will still work. But none of what you're saying would make any sense. So why should there be a natural intuition that is geometric here? Yes?
So maybe we can interpret him as, you number the nodes on your left as 1 to n.
Yes.
And then when you are going from n to something, then that number has to be less than.
Ah, very interesting.
That means it's going up.
Very interesting.
And
So
if
now
it's
what?
greater than that index, that means it's going down.
Okay, good. So what you're saying is that let's think of this geometrically in a different sense of just going up and down and not trying to quantify, how much or whatever, right? So then, but then what about his example? So every node I is connecting to I minus 1, and then 1 is connecting down to n. So now what happens?
Basically, get the difference and.
But now it works. Now it all add up nicely.
Yeah, they add up nicely.
So maybe there is something to this. Now I need to think. See, you got me now. So let me try to formalize the claim that is sort of bubbling up out of the room now. The claim is the following. Oh wait. Oh shoot, I think I have a reason why this claim doesn't make sense. But let me just tell the claim anyway. Okay? So the claim is that if I number the vertices 1 through n, and I now look at for each edge, I look at its number on the left and number on the right, and I look at the difference, the sign difference. So this side minus the other side, and I add them all up, it should sort of net to 0 or something. Right, because the number of things going up should balance the amount of going up should balance the amount of going down. Right? Is that kind of what your equivalent, your interpretation of it? Yes? No, what?
I guess in the given graph there are many edges.
Yeah.
And if we add them all, it won't make means. Maybe we can check if we are given a set, it's perfect or not.
Yeah.
But given all the edges, we can't find a perfect match.
Right. But what is your claim? I'm trying to find a claim here that characterizes yes or no that there's a perfect match. And it sounds like you were saying that you have to look at the differences as kind of a discrete slope and they should all net to 0. So my problem with this claim is that suppose I renumber the vertices now. Again, there's nothing saying I can't renumber. Instead of saying 1 to n, I could say 1, 7, 6, 5, 4. What stops you from doing that? Yes?
I think the problem is also picking the edges when you're adding the slopes.
Well, I'm only looking at an edge in the graph, in the input, and looking at the difference.
I understand that part, but when he said you have edges up and down,
Yeah.
he picked up edges such a way that they're adding up.
Yeah.
But picking those edges to add them up also is tricky.
Yeah.
You can have from each vertex which there's all I have edges to go into all the vertices from x to y. Then
So I'm not, my gut feeling based on all these arguments I'm making is that this is not going to work. But it's worth pondering whether there's some way to characterize it some of them. Let's leave it at that. Let's think about whether there's some way. So you're not allowed to use geometry directly because I can move the geometry around. You're not allowed to use numbering because I can repermute. So you have to have some other way of describing what's going on here. Right? Repermutation, you either have to argue that repermuting will not change the actual value, and that's plausible, or something else has to happen. So this is a little trick, right? I mean, if you have some intrinsic property of an object, and that intrinsic property doesn't change under trivial modifications of the input, then what you're saying should also not change under trivial modification of the input. Otherwise you have a problem somewhere. There's one way to think about testing out whether an algorithm makes sense. That's why I was initially like, Euclidean plane, I'm not so sure this makes sense. Because it's not, the graph has nothing to do with geometry, it just floats. Okay, alright. That's good. Let's move on. As I said, what I wanted to do was talk about variations on flow. So as I've said, over and over again now, a max flow instance consists of a directed graph, a source and a sink, and capacities on edges. And the idea is that you want to find a flow that respects all the capacity constraints, respects the flow conservation constraints. You don't add or subtract, and you don't manufacture or lose flow except the source and sink, and is maximized. But that characterization of flow is in some way very simple. It doesn't actually capture many of the other kinds of constraints you could put on a flow problem and still solve it using flows. So I want to go through a couple of examples of modifications to the basic flow setup, where with a small simple trick you can still run it, you run your standard flow algorithms and get an answer to the problem. Okay? And so the first thing is this. Suppose I have an instance now where I don't just have one source and one sink, but every vertex has demands that are either positive or negative. And one way to, the way to interpret these numbers is that it's the number represents the amount of material the vertex will consume and make disappear. So a consumption of -3 is a production of 3. A consumption of 4 is a consumption of 4. And a consumption of 2 is a consumption of 2. So I don't just have a directed graph and I have inputs and capacities. I also have these demands. Now remember with the max flow, there always was a flow, right? For any graph, I can always give you a flow. What is that flow? 0. Just 0. I just don't know anything at all. It was not a max flow, it's a flow. In a situation like this, you can't just put 0. Why? Why can't I just put a 0 flow to satisfy all the required inequalities here? So there's no source and sink. I'm just saying I want to assign flow so that all these constraints are satisfied. So the flow constraints, of course, are satisfied. The conservation constraints are satisfied. What about the demand constraints? If I put a flow of 0 on every edge, are the demand constraints satisfied? So the demand is not, I would like at least this much, at most this much, or at least much. I want this much, is what I'm saying. So if I put a flow of 0 on these two edges, the amount of flow coming here is 0. But this vertex sitting there with his mouth open saying, I want 4, give me 4. It's not satisfied. And this problem is not satisfied. So it is no longer a question anymore of saying, how much flow can you put? It is a question of, is there a flow at all for this problem? So the question of feasibility is the question here. I give you a directed graph where on every edge there's a capacity, on every vertex there's a demand. And I want to know if a feasible flow exists that satisfies the capacity constraints, the conservation constraints, and the demand constraints. And I would like to solve this using what we know about flows. Yes?
Can you explain what negative demand?
Yes. So a demand is the amount of, if I say that a vertex has demand 4, I'm saying that if I look at all the flow coming into the vertex minus the flow coming out, the difference must be 4. So this vertex is going to eat up 4 units of flow from what's going in and what's going out. Okay? So the difference from in minus out must be exactly 4. So if it's -3, out minus in must be 3, which means it's producing flow. So you can think of a vertex with a score of -3 as a pipe with 3 units of flow being pushed like a spigot that's coming out. You can think of a vertex with demand of 4 as a big hole of size 4 is going in. And you want everything to be, and you want these not to be true kind of, I mean up to the bound, but exactly true. That's the difference. With capacity, I'm not saying I want every edge to be full to capacity, right? When I put the flow in, but these I do. Yes?
Here, just this vertex is satisfied. All rest of them.
No, these numbers are capacities, they're not flows.
No.
These numbers are capacities. They're not flows. So right now nothing is satisfied. I haven't put a flow value in.
No, I'm talking about demand of each vertex.
Yeah, but it's not satisfied yet. I have not put a flow. Is there a flow that I can put? So by the way, is there a flow here that I can put to satisfy it? Any thoughts?
What's the label of each?
The capacity.
Okay.
Oh,
But we need to talking about flow.
Yes. Is there a flow assignment that satisfies all these constraints?
Yes.
Yes. Go ahead.
So you can push 3 on the top spigot, and then you can push,
So the top spigot, where does the 3 go? Which way does it go?
have to go to the, all 3 go to the bottom right.
To the bottom right? Yes.
And
Okay,
then
good.
2 of them will be consumed. And
Yes.
then push the remaining ones to 4.
Okay.
And then have the other one, it produces its 3. One of them go to the right, and the other 2 go to the 4. Add that all up right.
And so that one and that one satisfy this. So you get 2 coming in, 2 coming in, and then you get 4 total coming out. Good? You all agree? So there actually is a feasible assignment of flow values here. Namely, that one pushes 3 off on that side, this one pushes 3 off, split off into 2 and 1 here. That 3 and 2 go there, 2 gets eaten away and 2 comes out. And this 2 came in directly, so 2 plus 2 is 4. So they are pushing up 3, this is eating up 4, every edge capacity is satisfied. That edge does nothing. Good. So the question is, how do I do this in general? How could I check that this problem is feasible without inspecting it with this carefully? Can I reduce this to a vanilla Maxwell?
What do you do it?
Yes? The original Maxwell formulation.
Can you create a source connecting the negative and create a sink connecting the positive demand point? And
Okay.
the edges are just set to be the consumption.
The capacity would be the consumption.
Yeah.
So the solution that you're proposing is this. So the solution to this problem, namely, can we reduce this problem of checking feasibility to the problem of checking flow, is to do exactly what we do. Construct a brand new source, because in a regular flow problem you have a source, and connect it to all the nodes that have a negative demand. Because they're kind of like baby sources, right? So connect the big Papa source to all, or the big Mama source to all, see fit. And you have the baby sinks connected to a super sink. Okay? Okay, but now what do you do? And add capacity is corresponding to the amount coming out. So this is, if this is demand 4, you put capacity 4. This is demand 2, you put capacity 2. What is the intuition here? The intuition is that, well, you have this weird problem where these nodes are producing flow from nowhere, or they're sucking up flow into nowhere. Well, let's make it explicit. Let's not have it nowhere. Let's make it explicit. If they're pushing flow from, if they're getting flow from somewhere, let's make a source that's giving to them. If their flow is dying away somewhere, let's catch it and then super sink. But now what do I do? How do I check feasibility? I now have a flow problem. Do I compute a max flow in this graph? What do I do?
So my suggestion would be run a maximum flow.
Yes.
And we have a solution. And I will check for those edges if they have the full capacity.
Very good. So the proposed solution is, now that you have a regular flow instance with no vertex capacity demands, you just drop these demands now, run a max flow. And check if all the new edges are fully saturated. Okay, so it's not running a max flow to find the flow value. We're running the max flow to look at what the flow gives us. So let's again consider the easy case. Suppose in fact the flow values are saturated. Right? Then what does that mean? That means this vertex is getting 3 units of flow. That vertex is getting 3 units of flow. If you now remove the source, it looks like this vertex has just produced 3 units of flow, which we said it does. Similarly here, if it's fully saturated, 4 units of flow are coming out of here, 2 units are coming out of here, remove all this stuff. Now it looks like 4 units of flow are just disappearing at that vertex, which is exactly what we wanted. And of course all the other flow constraints are satisfied. So again, one way it's easy. If it is true, you can do it. But what if it's not? Suppose the max flow does not saturate one of the edges. Then what? Can we argue that there is no way to do this thing? So the trick with these things is to reverse the question. Rather than saying, oh, there's no max flow, therefore there's no feasibility. Say, suppose you had a feasible flow assignment. Can you extend it back to a true flow? Right? If you want to prove A implies A is equivalent to B, you can either prove A implies B and B implies A, or you can prove A implies B or not A implies not B. A implies B, not A implies B. So what we're going to say now is, suppose there was in fact a feasible flow assignment that satisfied all the demand constraints. Then you can rewrite it as a true flow just by saying, okay, just put 3 units of flow back. So either way, either if you have a flow, or if you have a max flow saturated, or if you have a feasible solution here, they're equivalent to each other. Yes?
But it doesn't prove that if I have a maximum flow, that it's not.
I'm not looking for a maximum flow. I'm looking for a flow that saturates everything.
Okay.
So I'm saying a flow that saturates those edges exists if and only if there's a feasible solution here. I've shown that a flow that saturates those edges will give me a feasible flow here. And now I'm showing you that a feasible flow gives me a flow that saturates those instances. And remember, what is the maximum flow possible in this graph? It's in fact the flow coming out of the source. I have to saturate it. That's why I'm computing max flow, right?
Yeah.
The only way to get a max flow is to saturate the flow coming out of the source. And by the way, I can check again, right? If this number is not equal to that number, then already I have a problem. I have too much supply and too little demand, or vice versa. So we know these two numbers are equal. We know that maximizing the flow will saturate the edges, and we want to saturate the edges. So it all makes sense. Okay, good. So you can now extend what we know about flows, the dictionary of flows, to problems where you're not trying to find a max flow, but you're merely trying to check feasibility of some problem where vertices have demand. Here's another formulation. Suppose that edges have lower bounds. So this is a little known fact, or maybe it is a well known fact, it just was little known to me, that when you're pushing oil through these Alaskan oil pipelines, you have to maintain a certain amount of flow. If it gets too low because the temperature, things start coagulating and start getting blocks in it. So since we're doing algorithms, let's think of this in the language of flows. Suppose you have to have a certain amount of flow on an edge. You're not allowed to have zero flow, for whatever reasons. And again, now a zero flow will not work. I can't put zero because some edge might say, no, you gotta have 2 units of flow on this edge. So now what do we do? So in this case, I've drawn it, I haven't labeled everything because it will get very messy. Look, that edge on the top left, I'm saying that its capacity is 3, but its lower bound better be 2. And just to make life difficult, I've kept in all my demands. Yes?
I changed the demands on the two verses, saying that one should be -1 and one should be -5.
What's the intuition?
The idea is I'm assuming that the two edges are two is always there and making the edge as 1. Like putting a bracket and then changing the vertices capacities. That way I already assume that there is one, then solve for the problem.
Good. In fact, maybe you'll be spying on my slides here. What do you take? Well, of course the notes are here. So this is the basic idea. And this is why I introduced vertex demands before. If there were no demands on this, I'd be having to introduce demands to say, why am I introducing vertex demands? So the idea is that if you have a flow problem which has lower bounds on the edges, saying that each edge needs at least a certain amount of flow on it, you can reduce it to a problem where there are no lower bounds on edges, but you have demands on vertices. Which, as we just seen, can now be reduced itself to a problem where there's max flow, but there's no demands on vertices. So we're creating a chain of reasoning. And in particular, the way you do it is by saying, okay, I need to have 2 units of flow on this edge, so I'm going to put 2 units of flow on this edge. And I'm going to put it by adjusting the demands accordingly. Notice that the two endpoints both had a supply of 3, because they were both pushing out 3. If the top one is pushing out 3, then 2 of that's going to go on this. So it's really only pushing out 1. If it's pushing out 2, 3 this way, a low bound is 2, so I'm pushing out 2. If it's pushing out 2 here, then this is effectively pushing out 5, not 3. Because it's 3 of its own plus 2 coming on this edge. So it becomes 5. And you can show now if I do this for every single edge, for every edge you take its endpoints and you adjust accordingly. Right? Maybe some capacitors go up and down and down. At the end you'll get a problem with no edges lower bounds and only vertex demands, which we know how to solve. And once we solve the feasibility problem for that, we just have to add back the flow that we implicitly assumes that. So we solve this problem and we say, okay, there's 1 unit of flow going through this edge. Effectively, that means that there are going to be 3 units of flow. Oh no, actually that's not true. No, we don't have to do that. We just leave it the way it is. You have to change the capacity as well, though, I think. Yeah, the capacity has to be changed to 1 because I already pushed 2 units of flow. So I can't anymore claim that it's capacity 3. It's going to have capacity 1. Okay? Okay. So again, we saw how to handle vertex demands. We studied how to handle edge lower bounds. Another trick you can do, and there are quite a few of these tricks, but another trick you can do now is to say, well, suppose it's not just my edges that had capacities. Suppose my vertices had capacities. So in other words, think of this as a bottleneck. Maybe there's a kind of a room where people are waiting, right? And there's flow coming in and flow coming out. There's a queue here, so people are going to wait in this room before they're processed for the next appointment. And the room is not very big. So you have to make sure that not too much flow is going through this room. Right? So this is different from an edge constraint. It's one thing to say that too much flow can't go on an edge, just like a pipe constraint. I'm saying here that the amount of flow going through a vertex is not very large, which means that the total of flow going in, cannot be too much. Okay, there's some capacity number of flows. Now what do I do? Can I reduce this to a standard flow problem?
Make the vertex to edge of.
Make the? Yes, go ahead.
We can put a edge of capacity 5 and connect it to other edges.
So, you mean like this? So this is actually very simple. For every vertex that has this problem, replace it by an edge that has that capacity. So now if you look at this configuration here, you can only have 5 flow going through this super edge here. That means there's only 5 flow going through the vertex. Maximum. Right? I could then say, oh, but I want to have at least 3 flow going through the vertex. And I just put a lower bound of 3 here. And now once I have a lower bound of 3, I have the previous technique to convert that to demands and the previous technique to convert that to reduced flow. So there's a whole cascade of modifications you can make to the flow problem while still keeping the basic algorithm the same, which is really a nice thing about flows, that they're very flexible. They adjust and you can incorporate all kinds of constraints on them. Not any kind, but all kinds of constraints on them. And still manage to capture your problem and just use this basic flow method. Which is why once you've learned your basic flow algorithm, you can apply it over and over again. It's just a question of adjusting these complex things. And these will cost you, of course. Doing these kinds of modifications, you increase now the number of edges by the total number of vertices in the graph. And that will happen, but that's okay. At least you can express it. Okay? So on Thursday, and that's in the notes, we will see applications now, how to take a problem that has nothing to do with flows and apply it. Apply flows to it, maybe using one of these special tricks. Okay, so I'll see you on Thursday.